Okay, everyone, let's get started. So, you all are working on Lab 2. That'll be due
Next Monday.
Monday. So it's too early to introduce the next lab. So I thought today I can review the material I talked about last week and also show you some tips for debugging and getting things working. Some things I'll go into a little bit more detail about the tools. So I've got Quartus up. I'm going to open. Now this time, by the way, I'm running Quartus remotely off of one of my lab machines. Did I kill it? There it is. Wait a second. Okay, so I'm going to open project data designs lights VGA. This is my most recent version, I believe. Hello. Here, hold on a second. I think I might have confused my X server. Yeah, it pulled up, but I don't have a menu bar. Hold on one second here. Close MOBA Extern. So if those of you that use Windows, like I do on my laptop here, I use a program called MOBA Extern, and it is a SSH client, and it also supports graphical applications that you run remotely. It's a little glitchy though. So I'm going to SSH to positron, run my .profile, launch Quartus. There we go, that looks better. Okay, so now I'm going to open project, data designs lights VGA. Okay, much better. Okay, so here's the top level module, and you can see I've got the key input, all the DRAM stuff, VGA, SRAM, and LED R and G, and then the Neo system is instantiated here. Any questions about this stuff? Is this clear? What's going on in the wrapper? Okay. Question? Okay, yeah, we'll get to that. Now if we go into Neo's 2, sorry, I meant to go to Platform Designer. So this is the system that we set up on last Monday. We've got the Neos processor, the pixel buffer for DMA, scaler, resampler, dual clock buffer, VGA controller, SRAM, timer, and programmed I/O for the lights. These may appear in a different order in your design. So this is the base system for the VGA stuff. The only thing I don't have that you probably have is the hex outputs for the 7-segment displays. Okay, so looking at the software. So by the way, I don't know if you noticed that I hit Control. I launched Quartus, but it was in the foreground, so I hit Control Z to push it into the background, and then I type BG to allow it to run in the background. You guys all remember that from 2.15? Did you learn that in 2.15? So basically that allows me to keep using this terminal. The same terminal that I launched Quartus in is now available for me to use for other things. All right, if I go to the directory where this project lives, lights VGA, and then I'll go to software lights and look at lights hello world.c. Now this is the I believe I had this in the lecture slide. So this opens up the pixel buffer device in the software. So this is the driver this is the way that you interface with the driver. You use this Alt-UP pixel buffer DMA open device, and you give it this string that points it to that device. And the return value from that is a handle to a pixel buffer DMA device, which I called my video. Then I check to see if my video is null, and if it is, I print an error message. If everything's okay, I go into this double loop where I say for all 240 rows and then for all 320 columns, I will draw a pixel at the location J, I. Remember, the J is first and I is second because it uses X, Y coordinates. X being the horizontal or the row, Y is the vertical. But if it's when you do a typical, for I for J loop, it's I is rows and J is columns. I mean, you could switch it if you wanted to. That's just the way I do it. So J is first, I is second. Does that make sense? Is anyone confused by that? Okay. So now this part is my image comes from the MATLAB script. So the MATLAB script generates a myfile.c, and this is setting up a global variable called myImage that is of type alt-U8, and it's an array. So it's an array of 8-bit, single byte pixels, 230,401 in length, because that is the 240 times 320, the number of rows times the number of columns. And it is being initialized with the image data. Right now we're seeing a bunch of 255s because this is the white sort of background that the cartoon cat is. Or actually, I'm sorry, this is not the cartoon cat. This is the Gamecocks USC logo, right? The C. I switched it up. And so this gets initialized in the section called read-only data because it is a global variable and it's declared as a const. Make sense? And then there's another file, myfile.h, which you include in your hello world.c, and it declares my image as an extern, meaning that it is and it's external. It's a global variable that is defined in some other C file. Make sense? So you don't have to write any of this. This should be generated by the script for you. But the point is that you can use my image anywhere in your code, assuming that you added the C file to the make file, which I have there was a command for that. It's a neos2-app-update make file. Yes?
For the script to convert the image, we were getting an issue that we're missing a package.
Yeah, so that's my fault, and I talked to the TAs about that. So I changed the script slightly from what we used to. We've used this script for years, and everything was fine. I changed it. I added a call to IamResize, and IamResize just resizes the image, and IamRotate. Very simple, functions, right? Well, apparently MATLAB won't allow you to use those unless you have they're part of the image processing toolbox. So if you use Octave, which is the free MATLAB, they're not in there. So there's a couple solutions. One, we actually have we have a university-wide full license for MATLAB. I think it works in the lab, so you could just use MATLAB instead of Octave. That would solve the problem. The other way to get around it is I added these files I sent a message out on Dropbox, and I just sent you these files that you can use directly. So you can just use the ones I sent you. The only reason why you'd have to use the MATLAB script is if you wanted a different image on your screen, which is fun to do, but not necessary for the lab. Yes?
I actually did download the script and then I went on the MATLAB, but every time I typed in the function and the name of the photo, it said it didn't work. It just didn't work, even the TA's on it.
Okay, I'll have
It
to.
just didn't work, even I put in like the correct name of the.
They didn't know what was going on?
It just said it just invalid function, like. For it.
Oh, that might have just been because you. Okay, I think I know what's causing that. When you open MATLAB, it has a current working directory. So all the functions that you can call from within MATLAB have to exist in your current working directory. So it's what might have happened is when you opened it, you may have to change your working directory to whatever directory that script is in. That might have been what happened. In fact, I can show you that right now. I can show you that right here. Got MATLAB on here. It takes a little while to come up. Yeah, it normally, I don't know about in Linux, but I know when you start the Windows version, it puts you into a default directory. Yeah, see the directory right up here. It put me in C program files MATLAB R2018A bin, right? You have to change this to, like if I hit the down arrow, these are all the different, I guess no, these are just the, oh yeah, these are previous directories I've used. You can just type in your directory, the directory where you downloaded the script, or you can just use the CD command inside the command window and change the directory. But I think that might be the problem. I think MATLAB may not be looking in the right directory for that script. In fact, can I just, I wonder if I can, I'd have to log into the lab machine, one of the lab machines, teaching lab machines to do that. But so give that a shot. If not, let me know if that doesn't resolve it. Okay, any other questions about the image file? Okay. Okay, so the command, by the way, was neos2-app-update makefile was the command that you use. You just do that one time to add that myimage.c into your makefile. And the command for that is in the lecture slides. Okay, all right, so what next now? So we've got the software. I'm going to go ahead and configure the FPGA. So I don't have an FPGA here, but it is attached to this machine I'm logged into in my research lab. So I'm just going to do neos2-configure sof, and notice I'm in the software lights directory. The soft file is up 2 levels, .. /output files lights.sof. So this is the command line tool for programming the FPGA. You can also use Quartus to do this, if which is the graphical version, if you want. I use both, just depending on what I'm doing. So now I've configured the FPGA, and so the next step is neos2 GDB server -- TCP port. I'll use 8005 and -TCP persist. Have you all gotten this working okay? GDB? So you start up the server. I normally just start it up with an ampersand, which will push it into the background. Hit enter. And then neos2 elf GDB lights.elf. And then target remote localhost 8005 and load. It's a lot to type, but once you've done it a few times, you get used to it. Now, a couple things you'll notice. These are the sections of the ELF file. So the ELF file is the executable file. It's the same format that Linux uses on any Linux machine. ELF files are separated into sections. The text section here is where your code goes. Then there's a read-only data section, which is where our image went, because I declared it as a const. And there's a read-write data for other global variables. And then there's an entry, which is a special section that defines the entry point for your code. It's where everything starts when you hit the reset button. It's kind of like you can think of it as the bootloader, the BIOS. Like when you start a normal computer, it's where everything begins. Now, pay attention whenever you load in here, pay attention to these addresses. Notice the address starts with 8 and has 1, 2, 3, 4, 5, 6 zeros after it. Because if something goes wrong and nothing works after this point, it may be because you have to update your BSP. Because if you go back to your system design and you look at the SD-RAM controller, I have to scroll because the resolution is lower because of the projector. But notice that here, let me scroll back to the left to make this clear. You see, this is the SD-RAM controller. This is the main memory that we're using for the code and the data, right? If I scroll to the right, the base address of that is 8 and 6 zeros. So this address is what's matching up to the address you see when you load your program. And the reason I'm pointing this out is because I've made this mistake many times where I updated addresses in the platform tool, and I forgot to update the BSP. And so when I went to load in the debugger, it loaded at the wrong address because the address had changed. Of course, you could solve this by just locking the address. There's a little lock thing here. You can lock that down. It's probably a good idea. Does that make sense? You guys all with me on that? Okay. So we got it loaded, and then I want to show you a few GDB commands because I didn't get a chance to show you these in the last 2 lectures. So if I set breakpoint, I'm going to use bmain. This will set a breakpoint at main, the main function. Once you set a breakpoint, you can type info breakpoint or info br. Just type info br. It's an abbreviation, and it'll show you all the breakpoints you have set. You guys, everyone familiar with what a breakpoint is? So the idea is that you set a location in your code where you want the debugger to stop when it reaches that line, right? So there's another command, bt, or backtrace, and that tells you what the state of your program is at this time. In other words, what's going on, what line of code you're currently at. Now normally, the backtrace is going to show you a stack. It's going to show you the stack of all the functions that have been called. But since I just loaded the program and everything is kind of fresh, right now I'm in how source crt0.s. .s means it's an assembly code file. Line 272. So this is the entry point. Everything begins in crt0.s. This name also comes from Linux, by the way. When you run any Linux program, there's also a crt0 that's part of Linux that forms the entry point to your code. You guys with me? Okay, if I type C now, by the way, I can see what's here. If I type L, oh, that's interesting. Disassemble. Okay, so that's weird. The L normally lists where you're at in the code, but I was in an assembly file, so it didn't work. So here's the address where I'm at right now. 28000020. And the first instruction that's executed is this move unsigned immediate. What is this all about? Well, again, if you go back to the platform design and you look at the settings in your CPU and you go to the vectors, that 20 is actually the exception vector offset is 20, and the exception vector is 80000020, right? So this is the exception vector. It's also where you start executing when you load through GDB. All right, now if I go back in here, I can, let's see, can I go N? Yeah, so N stands for next, and it steps, in this case, one instruction. And if you hit N and enter, and then you just hit enter, it'll repeat whatever the last command was. So I just stepped through, I was at the move, and then it did the init D, add I, branch less than, and so forth. Actually, it looks like it's going in a loop here because it did the init D and then it did the add I and the BGT and it went back to the init D. But this stuff isn't interesting because this isn't even my code. I want to get to my code, so I'm going to hit continue. And continue just lets it go. And it's going to go forever unless it hits a breakpoint or you interrupt it by hitting Control C. In this case, I had a breakpoint at main, so it went until it got to main. So whatever loop it was doing here at the beginning, it must have eventually gotten out of that loop, and it hit the first line of my main code. At this point, I can hit L now. Yeah, so if you hit L, which is list, you can list the lines around where you're at. So I'm on this line where I set new val to 3.0. It's line 24. And it shows like 5 lines before that and 5 lines after that. Okay. So what else can I do in here? I can print variables. I could say print new val, which if I hit next and then I print new val again, yeah, so originally it just had whatever the lowest double precision number is 3 point something times 10 to the negative 270th power. Once I hit N, it initialized that to 3, and then when I printed val again, I got 3. So what that means is that whatever line of code it shows you being at, that's the line that you're on, but you haven't executed yet. So it didn't put 3 in the new val until I hit N and went to the next line of code. Make sense? Did you guys do any of this in 146, 145 debugging? Did you do any debug?
We had MIPS and digital logic design in the earlier classes.
Like in Mars, the MIPS, yeah. So yeah, Mars has a debugger and Eclipse has a debugger. Visual Studio, all IDEs have debuggers. A lot of times they're graphical. In this class, we're just using the command line version, but they're all the same principle. You set breakpoints, and then you can step through lines, and you can inspect what's going on. For years, I didn't use a debugger. I would just put like print statements in to debug my code, and I would never go back to doing it that way. It's much easier to use a debugger. The other cool thing about this debugger in embedded systems is you have access to the hardware because we don't have an operating system. So we can actually read addresses directly from the hardware. So for example, if I go to this document I have on Dropbox, I have a link here to the video IP cores. This is a documentation for all the video blocks that we added in Platform Designer. So if you have any, if there's anything that if you're debugging and you want to find out more about how those work, you can look in this document. If we scroll down to the DMA, the pixel buffer for DMA, that's the character buffer, we're not using that one. DMA controller for video. So this shows, this little table here is showing the control registers for the DMA controller. The first one is the buffer address, and the next one's the back buffer address, and then you have resolution, status, and control. These are the control registers, the way that you would program the DMA controller from your software. So in GDB, I can actually look at those. So first thing I got to do is find out what the address of the base address of the pixel buffer is. So find that right. Let's see, there it is. The video buffer pixel DMA is 0, and that's at address 1020.1030. So in GDB, I can print. Now I'm going to have to use this. GDB uses C style notation, so I put the address in, and it's in hex, so I have to put the 0x1020.1030, and then I add the star that is a dereferencing operation, meaning I want to see the contents of that memory address. And I hit enter there, and it shows me that number, which isn't meaningful because I want to see it in hex. And when I put the -p-x there, it shows me the hex number. right? That's the contents of that first control register. And let's check to see if that's right. So what's supposed to be in there is the address of the back buffer, the default buffer is at 1 and 7 zeros. The back buffer is at 1 and 7 zeros. Why? Because that's what the SRAM is at. That's our video memory. 1 and 7 zeros. You guys see that? Makes sense? So what that means is I'm asking the DMA controller what its buffer address is, and it's telling me it's 1 and 7 zeros, which matches up not only to the setting that I had in Platform Designer, but also it matches the SRAM address that I'm using as my video memory. Likewise, I can add 4 to that address to give it the back buffer address, which is the same, because my front buffer and my back buffer are the same. By the way, if they were different, you can make them different. That allows you to paint pixels into the back buffer, and then when you're ready, you can swap them. That way, you won't actually see the pixels being painted on the screen as your software paints them. You guys with me on that? It's in other words, it allows you to prepare the video frame before you display it to the user. But we don't use that in this class because by seeing the processor actually paint the pixels is a useful debugging tool. That way you know it's working. Otherwise, you would sit there looking at a blank screen for a while, not knowing if it was painting in the back buffer or not. You guys with me? Make sense? So we use the same address. If I go to the next one here, if I go to 3.8, I've got F00140, which is what? What is that? That is, that's the resolution. So it's the resolution where the X is in the lower 16 bits and the Y is in the upper 16 bits. Is that right? Let's see. Yeah, 140 in hex. If I go to decimal, that's 320. Yep, that's right. It's supposed to be 320 by 240. And then, let's see, 1, 2, 3, 4. So F0 must be 240, I guess. Yep, 240. Everyone see that? So I printed it in hex. I put it in hex so I can split the two fields out of that value, the two separate binary fields, and then I plugged them in the calculator to convert them back to decimal, and I could see that it's 320 by 240. Okay, what else can we do in GDB? Okay, so we can use N, which allows us to step through lines of code. We can also use S if we want to step, but we want to step into a function. So notice the next line of code I'm about to execute is ticks equals alt-n ticks. Alt-n ticks is a function. So if I hit N, it's just going to go to the next line of code inside my main function. If I hit S, it's going to push down into that alt-n tick. So that way I can see what it's doing in there. So I'll hit S now, and notice now it says I'm in alt-n ticks at this location, alt-alarm.h. That's interesting. Line 112, and this thing just returns. The function just returns. It's just a one-line function. In fact, if I hit L, I can look at the whole function. Static, alt inline, alt 32, alt always inline, these always modifiers, alt n ticks, it just returns the number of the underscore alt n ticks. So alt n ticks is a global variable, right? So I can look at what that is right now. I can say print underscore alt n ticks, and it's 0. Well, how's it 0? Well, it's 0. It shouldn't be 0, right? Well, it's 0 because the way that works is there's an interrupt that fires every 100 microseconds that increments that number. But I never gave that interrupt a chance to fire because I started this up in GDB, and then I let it run as soon as it got to main, and I never gave that thing an opportunity to fire. You guys with me? Make sense? Right? So it's still 0. Now, if I want to get out of here, I can type fin, and that'll get me until that's like doing a step, except it'll run until it exits from the function. There's also a command called until. So I think I can do until. I can tell it to run until 34, for instance. Yep, there it is. So that way it'll run until it gets to line 34 in the current file. I can print my video. My video is a local variable. Look at it, it's just a binary, it's just a hex address. That's not very useful, but that's because I declared it as a pointer. But if I dereference it, if I type print star my video, now I'm seeing the contents of the video handle, and there's all kinds of information in there. It has the addressing mode, the back buffer start address, the front buffer start address, the X resolution, the phi resolution, the little character, the string, has a bunch of stuff in there that's stored inside that handle. Let's see, what else can I do in here? All right, so for I equals 0. So obviously with a for loop, it's not very, if it's a big loop like this, it's not very useful to try to step through it. So I'm just going to hit continue. And oh, by the way, you can type info registers. This is kind of cool. So I can actually print out all the register values, and you guys should all be familiar with these. These come right from MIPS. I've got the 0 register, which is register 0, always contains 0. AT, which is the assembler register. Then I've got registers 2 down to 23. And then I've got ET, BT, GP, SP, FP, EA. What the heck is that all about? Well, this is just register 24, 25, 26, 27, 28, 29, 30, and 31, all the way up to the return address. You guys remember that register 31 is the return address when you do a jump and link. So, and then the stack pointer, frame pointer, global pointer, ET and BT, I don't even know what those are for. And then there's the program counter, which defines where you're at in the code. By the way, I could change the program counter and force it to go somewhere else right now if I wanted to. I could just use the set command. There's also some special registers, status, exception status, B status, whatever that is, CPU ID, exception, a bunch of other miscellaneous special registers in there. Let's see, I can also type $PC, $PC, and that'll be just the program counter. So $sign denotes a register. Okay, I'm just gonna hit continue now. All right, so now what? It just hangs. So how do I get out of this? Hit Control C, and it'll stop it cold, whatever it was doing. If I type backtrace now, I can see that what it was doing was it was in this function called add floating point 3, and it was called from main. So this is not my code. So where did main call this function? Well, in order to figure that out, I got to hit frame 1. I got to go back to main, and then I'll type list. And you can see that was because I was doing something. I was doing this temp. I was at line 48 in main. So this line 48, I didn't call any function. But yet, when I interrupted it, it was in a function. It was in a function called add df3. So what was going on there? You guys, anyone know? Anyone have any idea? So I interrupted it. I checked the stack. It said it was in a function that main had called. I went back to main, and I was on a line of code that didn't call a function. Well, what's going on is that this line of code is doing floating point arithmetic, and I don't have any hardware support for floating point instructions right now on the Neos. The Neos doesn't do floating point unless you turn that ability on, which costs you some hardware on the FPGA. So instead, the compiler was aware of this, and it converted all the floating point arithmetic to function calls, software emulation. So instead of using the appropriate instruction, the hardware instruction, it's calling this function without me even knowing it. It just generated a call to that function without me ever calling a function, because that was the only way for it to do those floating point calculations. You guys make sense? Okay, so I'll continue again, and I think this eventually should end. Okay, now I hit I broke it again, and now I'm in a function called udivMod. Yeah, apparently main called a divide, so I was doing a divide, and I caught it doing a divide. Any questions about that? Okay, so I covered, let's see. These are in the slide, by the way, the lecture slides, but I covered the step command, the next command, the finish command, the list. List is L, just lists where you're at. F is frame, that allows you to go to so if I type backtrace BT and I use the F3, that'll get me to frame 3. So it'll put the debugger into a mode where it's looking at what line of code I was running in the main function as opposed to whatever's at the top of the activation stack. You guys with me? You guys clear with the stack? So the stack is there because every time you call a function, you put that function on the stack. And when I say that function, what I mean is all the local variables associated with that function and the return address. Right? Okay. All right. Let me continue again. I think this ends eventually. I'm waiting for it to end. I'm going to let it go for a while. Control C. Ah, there we go. So look, now I'm in an infinite while loop, which happens to be... Oh, look at that. My main function is completely gone. So you guys may see this too, by the way. If you return from your main function, there's nowhere for it to go because I don't have an operating system that could, find some other use of the CPU after main exits. So instead, it goes all the way back to AltMain, which is a wrapper around the main function. It calls main, and then when you return from main, it goes back to AltMain. Then AltMain calls exit, and exit just goes into an infinite while loop. It basically just says, okay, you're done, so I'm just going to sit here and spin and do nothing. You guys with me? Okay. Normally, you would just put that while one inside your hello world or inside your own main function. Or you'd have some other infinite loop like you do in your lab 1 code that just infinitely loops and updates the lights. Okay. All right, so the next thing I wanted to show you is debugging in the hardware. There's a tool inside Quartus. If you go to Tools, before I do that, let me delete this. Okay, I'm going to go to Tools and go to SignalTap. SignalTap Logic Analyzer. This is pretty neat. If those of you that are into hardware stuff will like this. When you first launch it, it's going to come up blank. I've already got stuff in it. Let me say new file. Here we go. So this is how it'll look when you first start it. This is a way to implement a virtual logic analyzer over JTAG. It allows you to probe signals inside the FPGA. And you can use this along with the debugger when you're debugging your, if you're doing software and hardware debugging. So, so the first thing, generally, the first thing you set up is the clock. So the way this works is that when you're monitoring signals on the FPGA, there's not enough bandwidth in JTAG to read them in real time. So instead, you set up these buffers on the FPGA that start recording the data whenever a trigger event happens that you set up, and then when the buffer fills, it sends the data back over to your host, and it puts it into a timing diagram. You need a clock that's used to sample the data that you're measuring on the chip. So over here, there's a clock. So basically use clock _50 here as your clock, and then you can set the sample length to, set it to 1K. This is the number of clock cycles worth of data it'll capture. And this is compressed because of everything is squeezed down here. And then over here you've got the ability to add nodes. So if you do a right click and say add nodes, nodes are the signals that you want to measure. So it brings up this little search window. You want to switch this over to pre-synthesis. And then hit, it says star, so hit list, and it should show all the signals at the top level of lights. Okay, so these are all my top level signals. it wouldn't make sense to try to capture clock 50 because that's my sample clock, but I'm going to grab everything else. So DRAM, VGA, SRAM, LEDG, LEGR, key. So you select the ones you want, you hit the little arrow there, it brings them over. And then over here in Neo system, these are all the signals that are in the Neo system inside your platform design. This is way too complicated. There's too much stuff in there. So if you want something in there, it's better to search. So what if we search for data _ master star and hit list, and I should be able to find that in there. Yeah. So these are all the data master signals from the CPU. I'm going to grab these guys and bring them in. So there's debug access, then read data valid, wait request, write, address, byte enable, read data, write data. Hit insert and then hit close, and then it should have all that stuff in there. Okay, so once you've added those signals, the other thing you could do is you could set up the hardware. So I'll set up USB blaster and select the soft file, which is in the output files directory. And then you can hit run, and it'll tell you that, do you want to recompile? So when you add these nodes inside of SignalTap, you have to recompile because you're putting these buffers inside your hardware. You have to regenerate the hardware every time you change the signals that you want to monitor. So I'll hit yes, and it'll say the file's been modified. Do you want to save your changes? Yes. stp1.stp is the file that, do you want to enable the SignalTap for the current project? Yes. The stp1.stp is the file that actually has this information in it that tells Quartus which signals you want to monitor in the virtual logic analyzer. So I will go ahead and regenerate that. It'll take a minute. So it goes back, even though I told it to recompile in SignalTap, it instructed Quartus, the window that was behind it, to recompile. So it's rerunning now. So if this works, I should be able to watch what's going on the DRAM interface, the SRAM interface, the VGA interface, and all the GPIO, the keys, the lights. I should be able to see that in a timing diagram, like a logic analyzer style timing diagram. Okay, I got an error. What's the error? Okay. Syntax error at lights. Oh, I'm missing an identifier here at line 3. Oh, apparently, there we go. I accidentally deleted DRAM address there. Okay. Save it and rerun it. I don't know by the way, notice that I got an error and I couldn't really see where it was, so I hit this button here. It filters out everything but errors. And I was able to get rid of all the other info messages and warnings and just leave the errors. Have any of you had any issues compiling? That's good. This semester is going very smoothly so far. You guys got Lab 1 up and running pretty easily? Huh? So that's good. I heard there was some bad cables. Is that true?
Yeah. There's a few boards that broke too.
Okay.
Push to them and like segments and stuff don't respond correctly. So if you like pushing different code to different boards, they would act differently.
Hopefully the TA took those ones out of circulation. Yeah, we have plenty of boards, so if there's any bad ones, take them out. It should be fine. Just have to identify them. Okay. In GDB, by the way, let's see, is there anything else we can, if you can type info variables. These are all the global variables in the code. Oh, I remember what I wanted to do, the nticks thing. So, by the way, now I've allowed this to run for a while. See, it's running. I hit continue. It's running an infinite loop, but the timer interrupt still interrupts even in that exit loop, or at least it should, to increment the n ticks. So if I hit Control C and type print underscore alt underscore n ticks, oh, still 0. Okay, well that didn't work out. I wonder what's going on there. I wonder if my hardware is broken. Well, that's a good question. So I've got the timer here. I've got my interrupt set up. It's set up on the IRQ, and then, oh, I might not have set it up in the BSP. So this is another troubleshooting thing. If you have the same issue, if I exit out of GDB and type Neos2 BSP editor, you need to make sure that you tell it what you're using the interval timer for. And so it'll generate the necessary, oh, I'm in the wrong directory, sorry. You can't run that in the app directory, you gotta run it in the BSP directory. You have to tell it that you want to use it as a, I forget what the term is. Let's see, we'll find out here in a minute as soon as it comes up. Yeah, see, there's the problem. Sys clock timer, I never set this timer 0 up, right? So the reason you have to do this is because by putting this setting in here, it's going to add an interrupt handler for that interrupt. Otherwise, it'll generate the interrupt and it just gets ignored. You guys with me? So that's what's happening. Is it was generating an interrupt signal every 100 microseconds, but there was no handler, so the Neos was ignoring it because I never set that up in the BSP. So I can fix that right now. Let's see, maybe not. Oh, there we go. Generate. All right, good. Exit. All right. Go back to the app directory. And, oh, actually, I'm going to go back to the BSP directory and do a Neos BSP generate files -- settings is in settings.bsp, and -- bsp - directory is dot. That's another long command. You'll get used to typing that out once you've done it a few times. And then I'll go back to the app directory and I'm going to rebuild the app. So I'll do another make, and there we go. And if I go back to Quartus, it should be done now. Yep, there, it's done. Okay, great. All right, so I'm going to do Neos configure soft // output files lights.soft, and it's going to give me an, oh, it worked. I'm surprised it worked because I was still running the, usually you get an error when you do that if you're running the GDB server. I'm going to kill that and reconfigure anyway. Oh yeah, actually it did fail, sorry. Notice it said operation failed. It said it was unsuccessful. So I typed jobs and I listed the 2 jobs I had running, one of which is Quartus and the other one is the GDB server. So I typed kill -9%2, which killed that GDB server, and then I reran the Neos2 configure soft, and then it completed successfully. So the FPGA is now running, and if I go back to SignalTap, I can run it. All right, so it's kind of hard to see with, I wish there was a way I could, can I kill that and kill that? There we go. Okay, so I don't have any triggers set up, so it's just acquiring as fast as it can acquire. But this shows you what's going on. I've got the DRAM column access strobe. You can see the DRAM columns being accessed. There's a DRAM clock enable, which is always high. Then there's a DRAM clock, and you're like, wait, what's going on there? That DRAM clock should be going. Well, the problem is that the DRAM clock frequency is the same as my sample frequency. And because they're both the same frequency, there's no way to see that clock going. So it's just going to show as being high, even though it should be. In reality, it's going up and down. There's the chip select, which is active, the write enable. I think the write enable, maybe not. Maybe I might not be writing anything. Chip enable, this is the SRAM signals now. Chip enable, a bunch of SRAM stuff. Then there's the VGA clock. The VGA clock is running at 25 megahertz, and I'm sampling a 50 megahertz, so as a result I can see the VGA clock. So there's the pixels, the pixel clock going out. And then if I scroll down some more, I can see the VGA vertical sync and horizontal sync, which they're so you can kind of see them going up and down there. The DRAM address, this is me accessing the DRAM, and then there's the key is F. Now, by the way, this is, if someone were to go up to that board and just hit one of the buttons, you would actually see that F change in real time, because that's what it's seeing on the keys. LED, G, and R are all zeros. SRAM address. Why is the SRAM address going so crazy there? Well, that's because it's accessing the frame buffer to pull pixels out and send them to the monitor. And then these are the actual pixel values. There's VGA blue, green, and red, and there they are. Those are the pixels going out to the monitor that are painting the screen on the monitor. Now this is not, obviously it's not fast enough to show everything, so it's skipping a lot of data because it's just capturing as fast as it can. But you can kind of get an idea of what it's doing there. And then I've got the master port on the Nios processor, and this is all the stuff the Nios is doing to access stuff. That's all right. So how do I use this? Well, first let me stop this thing. Okay, so say I have a problem with some peripheral, and I want to try to figure out if there's a hardware issue. If you go over to the Setup tab over here and you scroll down to the Data Master address, for instance, there's a trigger condition. Right now, all the triggers are set to don't cares. X is don't care. And the ones that are single bits have this little symbol here that means don't care for single bit signals. Okay, so if I want to debug, let's say I want to debug any writes to the LEDs. So the LED address is, if I look over here, I've got the parallel I/O right here, the last thing. LEDs is the export, and the address is 10201020, right? So I can actually set a trigger for a write to that address, and then I can see the instant that the Nios writes to it. So I just have to go back, I have to remember that address, go back to SignalTap and set the trigger to 10201020 in there and hit enter, and then I hit run, and then it says, oh, that's interesting. Didn't expect that to happen. If you click it, oh, by the way, the zero is where the trigger occurred, and then there's 128 samples that it's showing before the trigger and 896 after, and that's set up in that, I closed it, but in the clock window. So I'm capturing 1,000 samples, and I'm capturing a little bit before and a whole bunch after the trigger event. All right, so if you click on, let's see, let's load the code up because it's hard to, I don't know what it's doing if there's no program loaded on it. So let's load the program first. So I'll go to Nios 2 GDB server --TCP port 8005 --TCP persist, hit the ampersand, and then Nios 2 GDB, Nios 2 ELF GDB lights.elf target remote localhost :8005 load, and then are we good? No, we're not good. Okay, something went wrong. Maybe? Maybe not. Oh no, it seems okay. All right, let me break on main. Let me load again. Continue. Okay, no, we're good. Okay, so we're at main again. All right, so now the processor is frozen. The program is loaded, but the processor is frozen at the breakpoint. So if we go back to the SignalTap and hit run, okay, there we go. That's better. So it says acquisition in progress. It's waiting for that It's waiting for someone to write to the LEDs. The problem is that in my code, I don't actually have a line in my program that writes to the LEDs, but you can do it in GDB. So check this out. If I go back to, just to double check, see it says acquisition in progress and my waveform is blank, right? If I go to GDB, I can type set, and I can set a value for the LEDs. What's the address of the LEDs? Sorry, PIO 10201020. 10201020, and I can set it to be 1. So this will actually put a 1 on the LEDs. All right, so let's go back and double check. This says acquisition in progress. I go back to GDB, I hit enter, and then I go back and look, it triggered. So if I zoom in, you just click to zoom in and you shift click to zoom out. If you zoom in here, you can see that there's the 10201020, and it's kind of strange because it's supposed to be writing 1, right? But if you look down here at the write data, you don't actually see a 1. So where does it actually write the 1? Well, it turns out that, and I don't know exactly why it behaves this way, but that's actually not where the write happens. I triggered on that address, but I didn't trigger on a corresponding write signal. The write signal is right here. See this master write? And it's not high yet, but if I scroll to the right, it should go high at some point here. Okay, maybe not. Oh, there it is. Sorry. It took a while. So it took 73 cycles from the time that that address initially appeared on the data master address. But check it out. There's the address 10201020. So there's the write signal, there's the address I'm writing to, and there's the data I'm writing 1. Guys with me? So I was able to tell the processor using GDB, as opposed to my code, which is how you guys are doing it in Lab 1, I was able to force it to write to that address through GDB, and then I was able to trigger on that write on the Avalon bus transaction using SignalTap, and now I can actually see where that write happened in the hardware and see, and more importantly, see what was going on, what else was going on at that time. So this way I can confirm that I'm doing the write in the hardware. Make sense? So I don't know if you'll ever need this, but if you have a problem that's a tricky problem that you're trying to troubleshoot, and you've exhausted all the options in software, then you may have a hardware problem. This allows you to look inside the hardware and see what's going on. Okay. Okay, so now we've got, let's see, that's GDB, SignalTap. Anything else in GDB? By the way, this is the same GDB that you would use on any Linux program. The only difference is that I'm using the target command to connect to the board. If I don't use that, you know, like if I start up GDB and I try to set a breakpoint on main, and I hit N, it says the program is not being run because it's not being run locally. It's running on the board. So the target command is what connects you to the board. That gives you a hook into the board, what's going on the processor on the board. Okay, let's see, anything else here? The last thing I wanted to mention was, in the last lecture, Jason 313, source, lectures. Actually, lecture 1, or actually lecture 2, sorry. Well, lecture 1 too. Back in lecture 1, I've got a little cheat sheet for commands in GDB in there. So this is like an example of where I I did the target, the load, set the breakpoint. In this case, instead of breaking on main, I broke on hello world.c. One of the TAs told me that some of you guys had a question where you didn't have the same, your hello world.c line 39 was different from mine, right? And so that if you had that issue, that was the reason why. It would have been better to say, just break on main there, or use a function name to break on instead of a specific line number. But you can set line, you can use line numbers there too. Then I did a continue, and then I printed some stuff. And then I think I have a slide with like a whole bunch of, so there's the print command is P, or you can spell it out, print. Backtrace frame is what allows you to go back to another function instead of the top function that's currently run, one of the functions that was a predecessor that called the function you're in. Continue just tells it to go. Step over does a steps over functions. Next steps into functions. Finish steps out of a function. These usually represent buttons in Eclipse if you're using a graphical debugger. And then set a breakpoint, and then del is delete breakpoint. So you would say, delete, and you do it by number. Any questions? Okay, there's a lot of information too. If you need help, you can find lots of stuff online about GDB. In lecture 2, I had some slides here about some stuff that's specific to C. Yeah, so just to be clear, since I skipped this over in the last lecture, you guys all know Java, and you know C++. At least if you're in computer engineering, you've taken 145, 146, and 240. If you're in electrical engineering, you haven't had 240, right? So this is your first time using C or C++, right? Until you take 350. So there's a couple differences I wanted to point out. I'm not sure how many of these are going to be relevant. But it's important to know that in Java, everything's a pointer. Everything's a reference. So variables are addresses to the data that is being held in that object. Did you guys learn about that in 145? They just don't. They might not even go into the details. In C, pointers are explicit. So if you declare, like for example, if you declare an integer int a, when you refer to a, you're referring to the contents of a. On the other hand, you could declare an integer to a pointer to an integer int star b, which a pointer is an address, a memory address. But the thing about this that's confusing, and the reason I bring this up is because when you declare a pointer, you declare it with a star, but when you use a pointer and use a star, it's meant as a dereference, which is, you saw me use that in GDB, where if you do a star and then an address in GDB, that pulls, if you're referring to that, well, if you're reading the contents, if you're doing a command like printing, for instance, and you put star and then an address, it'll print the contents of that address. Likewise, if you use set, use set and use a star, then it will write into the contents of that address. You guys with me? C works the same way. The star is a dereferencing operation, meaning that if you put a star in front of something, it's saying, I want to access the contents of this pointer, of this address. And if you have something that's not a pointer, or even if you have a pointer, and you put an ampersand, that references it, meaning it takes the address of that variable. You guys with me? So there's star is dereference and ampersand is reference. So dereference takes a pointer and converts it into actual data that's at that address. And then the ampersand takes the address of something. Arrays are pointers as well. So if you declare something as an array in C, so if you say int a with 100 size 100 array, and then you refer to a, that's a as a pointer. So what's happening is that if you use brackets, like if you say a of 0, the brackets actually serve the same purpose as the dereferencing operation, the star. The difference, though, is that the brackets allow you to not only dereference, but to add an offset and then dereference. So if you say a of 5, it's going to take A as the base address, then it's going to take the size of whatever A is, so if it's an integer, the size is 4 bytes, multiply that by 5, which gives you 20, and then add 20 to the address of A, and then dereference it. Does that make sense? And then we talked about, multi-dimensional arrays. You can squeeze them down to one-dimensional, which I did mention that last time. And then typecasting. This is going to be important for Lab 2. And I think you guys probably learned about this in Java, right? Typecasting. So if you have a number like 2.5, in this case it's just a constant literal 2.5. It's interpreted as a double precision float. And then if you do it, you can in this case I'm taking the sign of that and assigning it to A, and A is declared as a float. So in this case you're taking sign, which is a double precision value. It's going to return a double precision, and it's going to put it into a single precision float A. Right? Probably not a good idea. I should have used the sign F, the float version of sign, instead of double. Or I should have declared A as a double, in which case I would have been consistent. You guys follow that? So A is a float, and then B, you can, if you want to round B down to the nearest whole number, you can use round F, and then the return of round F is a float, and then you would want to cast it, in this case, as an integer. So you would just use the parentheses, in this case, say alt U16, would convert it from float to an integer. Now you might say, wait a second, if I didn't have that typecast, if I just took round F and assigned it to B, B is declared as an alt U16, so wouldn't it automatically typecast it? And I think so. I think so. I'm not sure though. You're leaving that up to the compiler, which is dangerous. I would cast it just to be sure what's going on. You guys with me? Because you see, this is a float that you're assigning to an integer. If you typecast it, then you convert it explicitly. You guys with me? So why do we care? Why do we care about typecasting? Because in lab 1, remember that lab 2, you're doing image transformations in floating point, but ultimately you have to take those transformed locations and use them as indices back into another array, right? And indices are when I say indices, I mean, indexes, like array indexes like that. Those have to be integers. You guys with me? So you have to be careful with your typecasting. Okay, that's all I have to talk about today. Any questions? Any questions about GDB? Yes?
In Lab 1, we didn't have the interrupt timer, so how was it able to do the time delays?
Oh, that's a good question. In the original version of that lab, we did have the interrupt timer because I thought that it was required for the same reason you just asked. Like, how does it know how much time has passed, right? So I always had everyone put it in. And one day I decided to look into how the uSleep function works, the microsecond sleep. And it turns out it doesn't require the interrupt timer. The way it works is they wrote a loop in there, and they wrote it I think they wrote an assembly code because they wanted to know exactly how many instructions the loop body was. And from that, they knew how many clock cycles would go by in each loop iteration, right? So and there's a constant in the BSP called cycles per second, right? So the platform designer is aware of the clock speed, which I think is, I actually don't know where it gets that. I guess it's probably inside the settings here for this. Yeah. So notice it knows is 50 megahertz here. So the BSP knows that the clock is at 50 megahertz. So it writes in system.h, I think it's in system.h or one of the header files, it says clock rate, right? So the usleep knows what the clock rate is, and so it knows how many seconds per cycle, and it knows how many cycles it takes to go through one iteration of the loop. So they just calculate, based on how long you want to wait, they calculate how many trips through this loop they want to take, and then they just do a busy loop. So to answer your question, it's a busy loop. It uses a busy loop. The problem is that it only does the looping when you're in the usleep, which is a synchronous blocking function, right? So there's no way to use that information outside of that function. There's no way to track how many cycles have gone by inside your code. That's why we use the interval timer. But in the next lab, we're going to use a cycle. We're going to add another peripheral to the platform designer called a performance counter that'll actually just count cycles that we can access from the code. Does that make sense? So that way you can look at how many cycles passed at one point and then check at another point and take the difference, and you'll know how many cycles have elapsed in that chunk of code. Right now we can't do that, but we can use the interval timer to get an idea of how many ticks have gone by. Great question. That one actually, I was confused by that for like 10 years. Any other questions? Any other issues in lab? So we had some bad boards, some bad cables. Hopefully everything's been resolved. Hopefully the TAs are able to help everyone out, especially on Wednesday where it's a lot more busy. I think everyone's got a partner now. Everyone's submitted lab 1. Was there any issues with the submission tool, Praetor, Charles's software for submitting labs? And I think everyone's been being checked off too, right? So like I mentioned last time, as long as you submitted your lab on time, it doesn't matter when you demo your lab, but just be aware that you're not going to get a grade until you demo it, right? So if you work on lab 2 and you forget to demo lab 1, don't worry. You can, if you want, you can demo lab 1 and 2 together when you finish lab 2. I'm fine with that, but it's just going to delay us getting the grade back to you, right? And we're going to use the submission date on Moodle as to when you submitted it to determine any late penalties. Any other questions? Okay, great. Well, we'll see you in lab later this week. Thank you.